So far, we've been looking at what happens to oxygen and how it's loaded and transported and unloaded, but we also need to think about what happens to CO2. And if we're looking at CO2, then we should really start where CO2 begins, and it's formed by the cells. So let's go down to the cells in the tissues and notice that when cells use oxygen, they also make as a byproduct CO2. And that CO2 will diffuse down its gradient and out of the cell into the interstitial fluid and then into the plasma. And when it diffuses into the plasma, three things can happen to it. First of all, about 7% of it can stay in the form of CO2. CO2 has some solubility. It's 20 times more soluble than oxygen, so it can dissolve a little bit in the plasma. So here we are, CO2 is dissolved in the plasma, just a little bit. Circle that. About a quarter of it, say 23% actually, will enter into the red blood cells and bind to hemoglobin. And you know about that. We've talked about that before. It binds to the globin portion and knocks off CO2. So there it is inside the red blood cell. But most of the CO2, so the remaining 70% of CO2, will go into red blood cells. But once in the red blood cells, it gets converted into bicarbonate ion, and then it once again exits. So it actually exits as bicarbonate ion, and that's because bicarbonate ion is really very soluble in plasma, and it's really easy to be transported that way. So you can see from the notes here that we looked at CO2 being a byproduct of ATP production, and I'll just make a note that this is where we started in our picture, and in our notes this is where we start. CO2 then diffuses down its pressure gradient and into the plasma, and there three things can happen to it. Either it's dissolved in the plasma, or maybe about a quarter of it is bound to globin. And when it does so, we call it carbaminohemoglobin. And finally, the majority of it goes into the red blood cells and is converted to bicarbonate ion. So what I wanted to show you is just what happens inside that red blood cell. So here I have that same picture, just the red blood cell drawn a little bit bigger, so we can focus on what's happening inside. So here is about 70% of the CO2 entering into the red blood cell. And in the red blood cell, it can combine with water in a reversible reaction. So this means the reaction can go in either direction, and it can become carbonic acid. It can happen just by itself, but if there was an enzyme available, and this enzyme actually is carbonic anhydrase, and Ca stands for carbonic anhydrase. Notice it ends in ASE, so that's the enzyme. The enzyme makes it happen about at least 10,000 times faster. So the reaction happens really quickly, and because at this point there's lots of CO2, although the reaction can go in either direction, the large amount of CO2 pushes it to the right, and carbonic acid is formed. Carbonic acid is a weak acid, which means it doesn't really hang out in that form for very long. Quite a lot of those molecules can actually fall apart or dissociate and form hydrogen and bicarbonate ion. So some of that hydrogen that's formed, I'm going to highlight that hydrogen, some of that hydrogen that is formed is immediately buffered when it binds to hemoglobin. So I'm just going to make a note about that up above. Some hydrogen binds hemoglobin and is buffered. And that's great because anything that doesn't bind hemoglobin would actually leave the red blood cell, and it can decrease blood pH and affect pH levels, because that's what hydrogen ions do. But not only is the fact that some of that hydrogen binds hemoglobin and is buffered, and so is kind of kept away and kept from changing pH, but that's really handy because remember, hydrogen binding to hemoglobin is one of those signals to hemoglobin to drop off oxygen. So hydrogen binding hemoglobin also signals hemoglobin to drop off oxygen. You want to bump off oxygen, so this is the Bohr effect. So that takes care of the hydrogen. The bicarbonate ion doesn't stay inside. The bicarbonate ion also leaves, but when bicarbonate leaves, it actually switches places with another ion, chloride. So when bicarbonate exits, chloride actually enters. And the handy thing about bicarbonate, not only is it really soluble, but it also acts as a buffer, and it buffers the blood. So this little thing where bicarbonate exchanges places with chloride, we call this the chloride shift. And it can go in either direction, either bicarbonate in and chloride out, or bicarbonate out and chloride in. In this case, at the tissues, bicarbonate is going to be exiting and chloride will be going in. So in this case down here, it will be when bicarbonate exits the red blood cell and chloride enters the red blood cell. So now you know where the bicarbonate comes from. Let's just take a look at back where we are. So we have these three forms of carbon dioxide now, and as we return, this is part of the deoxygenated blood, as we're returning this deoxygenated blood to the heart, to the right side of the heart, let's just keep track and draw pictures to represent what we have. So less than 10% of the CO2 is in the form of CO2 gas dissolved in plasma, so I'm just going to draw it like that. About 20%, so I'm going to draw two things represented by CO2 binding to hemoglobin. And that's going to be inside the red blood cells. And this is all going to be part of deoxygenated blood, so I'm just going to highlight that and remind us that it's deoxygenated blood. But the majority of CO2 is transported just as bicarbonate ions. So 70%, so I'm going to draw 7 of these bicarbonate ions to represent 70%. And these will all, this deoxygenated blood, they will all return to the right side of the heart, and then the right ventricle will pump it out to the lungs. And as we go to the lungs, then we'll see what happens and how we get rid of CO2. So I think I'll show that in the next video.